in the back, coming around right now is Kenny Katara. He's been in our department for 30 years. We got Larry McHenry in the back hiding out there. He's been with us for 29 years. And we got Brian Mills. He works out of our Southwest Center. He's been with us 17 years. One of the most important aspects of our job every day that we utilize is personal protective equipment. You'll notice that Larry's taking some of his out. Every morning before the job, they have to get out their gear and they check it because their life is on the line. And he's doing a seal test right now. He'll seal up his glove with air and check it for any pinhole leaks. Very important. One of the other things that we use are hard hats. You'll notice they're wearing boots on top of their regular work boots, and then eye protection. Larry also is wearing what we call the personal voltage detector. And these devices are designed, and if they're working out in the field, they're walking around, and there's any energized lines, this thing will actually start to beep. You're going to hear them energize the system in a little bit, and this thing will start to go off. Larry's going to give it to me so we can take it off and put it out of the way. Otherwise, it'd just be distracting through the whole thing. All right, Kenny just energized part of the system. One of the safeties that we have in place is there's a little foot pedal right in front of Kenny's foot here. And he's going to control the voltage. Brian's going to be in the back on the main switch. He's going to kill it out. And then Larry's going to be operating some switches. We're going to give you a basic breakdown of our distribution system real quick. Okay, and here we have a capacitor for voltage support and power factor correction. We have a transformer. This transforms our voltage. We're feeding this thing right now with 120 volts. We're back feeding it on the top side. We're going to have 7620. Right here we have a cutout that contains a fuse. That's going to protect the system in the event of a fault. We have an insulator that isolates our conductor, because most people think our conductor is insulated. It's actually just aluminum wire that sits on top of this insulator that's attached to our pole. What he pointed out just there is what we call a sleeve or a snake. It sits over the insulator while they're doing work so they don't inadvertently come in contact with it. Okay, and you're going to hear them communicate. It's important when our guys are in the field that they communicate constantly so everybody knows what everybody else is doing. So you should hear them talking, and if they're not, then we're not doing our job right. All right, Kenny's going to go ahead and check. Everything's clear. All right. So right now, Kenny's going to show us, so this is a worst case scenario now. This should never happen in our system. So you can hear now we know Larry tells us the thing is live and his personal voltage detector is going off. And Kenny's favorite part of the exercise is showing you what an arc looks like. And notice, and the whole time, there he goes, he killed it out. You've seen the lights flickering. Whenever there's a fault in our system, power is being drawn towards that fault. So the voltage at your house or your residence or at your work may be decreased enough where the lights actually flicker. So we're going to run through a couple of scenarios on what we can run into. Obviously, safety is first. You're going to see them. They're going to do some switching real quick. One of the things I wanted to share with you is when we have a fault in our system, you have anywhere between 1,000 to 10,000 amps available fault current. And does anybody have any clue on what kind of current that it takes to kill us? Because it's not the actual voltage that kills us, it's the current, because it causes our system to, our heart to, I always mess this word up, defibrillate, to not beat at the right rate. So about 0.7 amps is all it takes to kick our heart off its normal frequency. And so 0.7, and we can draw anywhere from 1,000 to 10,000 amps on a fault in our system. All right, so one of the important things we talked about earlier is personal protective equipment and why they have to check their equipment when they're working. So Kenny's got a snake up here, and it's important when they put these up, when they're working on the lines, that they're in good shape so they don't inadvertently come in contact with the line. So he's going to show you worst case scenario. Again, all this is worst case scenario. This should never happen when these guys are working on the line. We said Kenny has about 30 years experience. And it takes, our journeymen, before they become journeymen, and it's a very distinctive noise. If you hear it once you hear it, it draws your attention. And one of the other things, he's growing that plasma, and I want to talk about, that's actually an arc, and we have an arc or arc flash. The temperatures that are generated right there are in a range of between 30 and 40,000 degrees. Now, put that in context, the temperature of the surface of the sun is only about 10,000 degrees. So there's nothing made by man that can withstand an arc. Basically, it's going to take metal to a gas state, from a solid state straight to a gas state, and it's going to return. And when it returns, you have basically shrapnel. Okay, so when it's important, you notice on the snakes that they have some writing on there, and they have these things checked. They have to have them checked frequently. And if there's any concern, they just take them off the truck. We have a group at our company that tests all these rubber goods. What are we moving on to? All right, so we talked a little bit about when Larry had his gloves out and he rolled them up and he did an air test. The slightest pinhole can allow for that voltage to come through. Now you're talking on our system, we have two voltages on our distribution system, 7620 and 1992. So 19,000 volts or 20,000 volts and almost 8,000 volts. And these gloves are tested at 50,000 volts. So Kenny's going to run us through. One of these gloves may or may not be good. And so he's got a ground on the inside of the glove, and he's going to run his lead there over the gloves, and we're going to watch what happens. Make sure everything works okay. And again, Kenny likes to draw an arc, and it always bothers Eric because. All right, so he's running in between all the fingers. That one looks like it's a good one, so that's a good thing. So again, these guys' life depends on their rubber goods. Yeah. So, and that was pretty distinctive when he hit it. Now, think about it. We're talking about, 1,000 amps, and we already said 0.7 amps will kill you, 1,000 amps. And if it doesn't kill you, it's going to leave you disfigured, to say the least. We've actually got inside of this glove, we've got a little holder, we've got a hot dog, and Kenny's going to pull it out, and you can see the damage that it does to this hot dog. And it kind of constitutes a finger for us, so you guys can get an understanding of how dangerous this is. So when you're working around our utilities, or if you come across and there's down lines, don't go anywhere near them, because we talk about when that voltage comes down to the ground, it can actually energize the ground at that 7620. And say you were out there and you guys were digging and the lines came down and it dropped on the vehicle that you're operating. Would you stay in the vehicle or would you get out of the vehicle and try to escape?
Stay in.
Stay in the vehicle, right? Unless you absolutely had to get out because the vehicle was on fire. Wait till we come there. Now, if you had to get out and there's a line on the ground, there's a couple of ways to get out of there, right? When I tell you, if the line fell right where I'm at, the voltage right at my feet is 19,920. When I take 3 steps away, it drops about 2,000 volts. When I take another three steps or 3 feet away, it's another 2,000 volts. Now, the reason why I tell you this is because current flows on difference in potential. So if I'm 19 here, and I step here, and this foot is at 17, now I have a difference in potential, and that current is going to flow through me. And as soon as that happens, we're talking thousands of amps. 0.7 amps kills you. Thousands of amps probably going to do it. So if you ever get around and you see a downed wire, 2 ways, right? Never pick your feet up off the ground, slide them, right? Just slide your feet, never lifting them up. And then the second, and this is the one everybody always asks about, this is the most masculine way to escape a downed wire. Both your feet together, and literally just bunny hop out of there. I did that for the kids, and now every time I do this, everybody says, do the bunny hop, do the bunny hop. One of the things that we run into a lot, especially with the rainy seasons that we've had in San Antonio this year, is we get a lot of tree growth. And we have customers and even contractors that will try to clear the lines for us. Now, trees are made of wood, Wood doesn't conduct electricity, right? Correct, wrong, whoever said that. At the voltages that we operate on, we can get this tree to conduct electricity, and you're gonna see it when Kenny makes the contact. Now the problem is a lot of people have this in their head that wood isn't a conductor, and normally it's not. So if it crosses the line, they'll get up there and they'll try to pull it down, or they'll try to little handsaw and cut it down, and it inadvertently come in contact with our lines. Now again, 7620, 19.9, depending on what side of town you're on. And once again, the voltages aren't what kills you, it's that current. 0.7 amps will restart your heart. Thousands will basically cause your heartbeat to change from 60 beats a second to 3,600 beats a second. And so that usually doesn't work out well for us. All right, so when we get a call, and we always tell our customers, if the line is touching, if the trees are touching a line, call us. We'll come out and trim the trees. We'll come out and de-energize the line to protect them. All right, so Kenny's favorite part of the job, watch Eric cringe every time this happens. It's awesome. And I like to stand back here whenever he gets to this point. And what happens is, you see, it's just sitting there smoking and smoking and smoking. The current is actually coming down through there, and what happens? The fire happens, and then the tree branch falls, and then, Kenny, there it is. I knew he was going to do it. And so the tree branch catches on fire, maybe falls on the house and burns the house down. So if you see any of these, make sure you contact us, let us know. If you guys are working out there, give us a call. Hey, Brian, we got a bunch of trees in the line over here. Can you get somebody out there? And we actually have crews that'll go out there and do that. One of the big things that we run into in the spring and the summer, and you notice on the backside there's a balloon. And one of the things I always get asked is the birds. How do we get them trained to stay there the whole time when Kenny's making that arc? Eric purchased those for us, and Kenny always tries to burn them up, and Eric gets mad. But I was talking about back in the spring when the weather starts to change, kids are out flying kites. It's just what it is. It's a thing that we deal with. And I always tell the kids, when they learn about electricity, they learn Ben Franklin with the kite and the string, and he hooked up with lightning. Now, Kenny's going to show us what happens if they happens to be flying a kite in your backyard and the string comes in contact. Now, watch where the string lets go. This is to let us know that the string is actually conducting electricity. Watch where the fire starts. See, right in the middle, that tells us that it's not actually at the bottom, it's right in the middle. That tells us that current is flowing right down that. And then, so if our kids get hold of that, they're basically coming in contact. Kenny? Fire! There's the fire marshal. Okay, so, and that's why it's important, even if we're smart enough as adults that we take this education and we give this to our kids, to the little ones that we know, even if we don't have kids, maybe our nephews, maybe our neighbors, just make sure they know, if you come in contact with that line, how dangerous it is. 0.7 amps stops your heart. Thousands of amps will definitely realign your attitude. All right, Kenny, where are we off to? All right, so it's birthday season, and we go to H-E-B and we buy a Mylar balloon. These are really cute because they're shiny and they're really great. The problem is, for us, is they're made out of aluminum. This happens to be the same material we make all of our conductors out of. So now you get these end of the line, you don't just hit one of them, 5, 10 of them, a big old group of them, and watch how well this thing conducts electricity. I'm going to stand back here. I'll say it, Eric. Kenny! So, and people don't think about this when they let these go, and the kids think it's cute and they see it. The problem is, is if it burns up there long enough, our lines are going to fall. And then we talk about that incident that I talked about earlier when those lines are on the ground and what happens. You know, and I try to make sure we get this information out to those who are going to need it. And all y'all who work with us or work around this utility stuff, you're going to need to know this. And it seems very simple to us now as we're sitting there looking at it, but until the first time you seen that arc, you didn't realize how much power was there and how much temperature. And the funny thing is, I've been doing some research on electrical safety, and it's not really the contact that kills people. It's the other things that come from that contact.